Good day, statisticians. So here we are reviewing for the AP exam, and like I said, this week we're reviewing some probability. So thank you for engaging in this asynchronous lesson. But here we're just going to do some problems, and we're going to focus on some kind of problems that are a little bit different than the ones that we had focused on in class yesterday. So let's start with this. This is again a very standard testy kind of question for statistics courses. Josephine travels to school by bus on 80% of school days and by car the other 20%. The probability that she is late is 0.05 if she travels by bus and 0.01 if she travels by car. So we want to know, on a particular day, Josephine is late for school. What is the probability she traveled by bus? Now, whenever I do probability questions, I always want to think, is there some way that I can kind of like diagram the probabilities, sort of organize my thoughts? And remember that there was always two types of diagrams. Trees, or Venn diagrams are the typical ways that we would diagram given probabilities. In this particular case, you might wonder, well, would a diagram be helpful here? And I would say yes. In this case, I would use a tree. Why? I have a bunch of conditional statements. I have a bunch of conditional statements where they're based on like different assumptions about the world. Venn diagrams are particularly useful if we're given a bunch of intersections. So we're given a bunch of overlaps between two different kinds of events. But in this case, it's not so much overlaps, but I have like different descriptions of of the probability that something happens given that something else does, right? So here, what do we know about Josephine? First of all, we know that and so I'm gonna make a tree. We know, first of all, that there's basically two ways that she gets to school here, according to this description. She either takes the bus or she takes the car, right? And then we know more information about her based on whether or not she takes the bus. So in a world where Josephine takes the bus, sometimes she is late and sometimes she is not late, right? And similarly, when she takes a car, sometimes she is late and sometimes she is not late, right? And now filling in the branches of this this tree diagram will communicate the probabilities that these events happen within these worlds, right? So just if we look at the world itself in the big scheme, good old Josephine taking the bus, there's an 80% chance she takes the bus and a 20% chance she takes the car. And then, now I'm going to focus on just the world where she takes the bus. Well, in this world, she is late 5% of the time, right? And so how often is she not late? 95% of the time. And notice that those add up to 100% because that's every single possibility in that world. In the world, given that she takes the bus, she's either late or she's not late. And those are the probabilities. Similarly, now let's look at the other world. She takes a car. Well, if she takes the car, she's late 1% of the time and she's not late, therefore 99% of the time. That makes up all the possibilities within that world. So this tree diagram really nicely summarizes the key things that are going on in this scenario. So now let's go to the question itself. And the question ultimately wants us to answer this, right? On a particular day, Josephine is late for school. What is the probability she traveled by bus? Okay, well, what kind of question are we asking here? Well, this is a conditional question. We're given something. We're given on a particular day, Josephine is late for school. We want to know the probability given that she is late for school. Now you might say, Mr. Zach, there's no like word given there. There's no if. There's no like when. There's no assuming. There's none of those like key words. Well, it's just the logic of the statement that tells us that that's a conditional. You're told on a particular day, Josephine is late for school. So now we're in a world where she's late. What's the probability? She took the bus. So here, notice that the world in which she's late isn't like one of the branches of this tree diagram. It's like the end of the branches. So we can't just read this probability from the table. We'll actually have to do some math. And so because I know I need to do some math, I'm going to convert this over into a couple of other probability statements, taking this bigger problem and breaking it down into smaller ones. So I know that a conditional probability, A given B, is always the probability of their intersection divided by the probability of the condition, right? Or the assumption. So it's going to be, in this case, the probability she takes the bus intersected with being late divided by the probability that she is late. So now we just need to figure out these probabilities. And I always like to start with the denominator. Let's start with the denominator. I want to look at what's the probability that we end up in a world in which Josephine is late, right? What's the probability we end up in a world that Josephine is late? Well, we'll see lateness occurs in two different places. She could either be late having taken the bus or she could have been late having taken the car. So we need to figure out the probability of each of these two mutually exclusive outcomes and sum them. We agree that her being late having taken the bus and her being late having taken the car are two different worlds and they're therefore mutually exclusive, so we could sum those two probabilities up. So what's the probability she was late given that she took, what's the probability that she was late and took the bus? Well, we just followed that path. Well, we see the probability of that path was 0.8 times 0.05, right? The second path we see is, let's see, there was a 20% chance she took the car, and then given that she took the car, it's 1% chance. So the probability of her being late in that, being in that world and being late is 0.2 times 0.01. And so what we can do is we can get these two probabilities, sum them up, and that will be the probability of lateness. So I'll go down here and I'll just write that down here. The probability of late, oop, someone's printing something. That would be 0.8 times 0.05 plus 0.2 times 0.01. And of course, I'll put the other in a calculator in a minute. But now let's get the numerator. Now the fun part about the numerator is always one of the two parts of our denominator. Remember, all probabilities are like fractions, it's parts out of wholes. So I need to say, okay, bus intersect late, that was one of these two calculations right here. Which one was it? Well, that was this guy, bus intersect late. So I can just take that probability, 0.8 times 0.05, and that becomes my numerator, and now I just throw it in the calculator. All right, so let's do that, right? We could say, okay, calculator, let's do 0.8 times 0.05, right? That'll end up being my numerator, 0.04, and then I'll add to that 0.2 times 0.01, which is 0.042, and so if I do 0.04 divided by 0.042, I get, whoa, really high probability. We could write that as a fraction. Actually, as a fraction, that's really nice to write. That's 20 out of 21. So extraordinarily high probability that if we know, if we're in a world where Josephine is late, the probability she took the bus is really, really, really high. If she's late, there's nearly, almost guaranteed, 20 out of 21 times she would have taken the bus. So there you go. So that's a nice practice. That's a kind of straightforward thing. And so really what we're reviewing here is doing trees, right? Using a tree diagram to calculate some probabilities. This is one problem. Let's take a look at a couple more problems just for more practice. Let's get into more like an algebra, more of an algebra kind of problem now, where we might combine trees and maybe even think about Venn diagrams a little bit as well too. So let's just try another kind of problem here. So let's see here. Let's say we were told we're given that the probability of A is 0.4. Then we're also given the probability of B given A is 0.2. So bing, 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 bing. As soon as I see that, I immediately start thinking that I could use a tree because I know about the probability of A, and then I know about the probability of something that happens given that A happens. So I can immediately see that I can start to symbolize this with a tree if I wanted. And then I'm also given, ooh, thrown an intersection there. Now, since I see an intersection, I might think that I could use that with a Venn diagram, right? And so maybe I'll end up using both a tree and a Venn diagram here, but I'll definitely start with a tree to get me going. So I have these probabilities. What do I want to know? Let's find the probability of not A given B. All right, well, let's strategize backwards here, and then we can figure out how we can use trees and Venn diagrams to maybe figure this out. Let's start with what we ultimately want to find, right? We want to find the probability, right, of not A given B. Well, the first thing I'm going to do is I'm going to take that and I'm going to write that as a formula. That's going to be the probability of not A intersect B divided by the probability of B, right? That's just how we convert a statement like this to a formula. Now, as soon as you see that, hopefully your little statistics spidey sense goes off and you realize, well, this problem isn't nearly as complicated maybe as it looked before, because this top value, the probability of not A intersect B, well, that's just one of my givens. I've already been given that fact. I already know that that is 0.3. I can see that. It's written right there on the screen, right there, right? And the only thing that I don't know is ultimately the probability of B, right? Now, if I knew that these two events were independent or something like that, then I would say, oh, since the probability of B given A is 0.2, then that should be the same thing as the probability of B. But I don't know anything about independence here, so let's figure it out. Our goal is to find the probability of B. So let's say let's just make a tree diagram to help us try to figure this out, because we've got a bunch of facts about A and a little bit about B here as well too. So let's see how we might be able to figure this out. So I know the probability of A was 0.4, right? I've got that there. And I know the probability of B given A is 0.2. I'm making the probability of not B given A is 0.8. I know the probability of not A should be 0.6. And I don't really know anything about these branches here. But, notice though that the probability of, let's go to the Venn diagram now to help us picture what we really need. So if this is A and this is B, I know that the probability of B is this guy right here. It's made up of two parts. The probability of B is made up of the part of B that's shared with A, this part right there, and it's also made up of the part of B that's not shared with A, this part right there. Well, the part of B that is shared with that is not shared with A, we know is 0.3. That's actually one of our givens right there. So essentially, all I really need to know is to find the probability of B is to find the intersection between A and B. Well, guess what? That's just like the last problem. I can find the intersection of A and B by following the path. The probability of getting A and B is say, okay, we're in a world where A happens, and then what's the probability that B also happens? We can get that just by following that path right there. 0.4 times 0.2. And so we can say 0.4 times 0.2. I mean, I shouldn't need to put this in the calculator, but I'll just do it anyways. 0.4 times 0.2, you get 0.08, right? So 0.08 is going to be this part of the Venn diagram right there. And so we can see the total probability of B, the probability of B altogether is going to equal 0.08 plus 0.3, in other words, 0.38. So Shazam, I've got 0.3 divided by 0.38, and I can just calculate that guy, and here we go. 0.3 divided by 0.38, and I got, well, that's kind of ugly answer. Let me see. Ooh, that's better answer, 15/19. Right? I always prefer, if I can write it as a nice fraction, as opposed to writing it as something else, 15/19. So the probability of not A, given that B occurs, in a world in which B occurs but A does not, B occurred, what's the probability A did not, is 15/19. And there you go. So notice that technically, I mean, I could have figured this out. I could have figured this out without using a tree, and I probably could have figured this out without using a Venn. But actually, in this case, using both of them kind of helped me navigate the problem in a kind of nicer way. Beautiful. Let's do one more practice problem for these general rules of probability, shall we? We shall. All right, so let's look at this guy. One more problem. Let's see here. About 5% of tires produced at a factory have a defect. Ooh. As soon as I see that, I'm already starting to think in trees. I'm like, ooh, there's some tires, 5% have a defect. I'm immediately like, in my statistics spidey sense is saying like, ooh, 95% don't. But let's see what happens with the problem. All right, so we know 5% of tires produced at a factory have have a defect. I just noticed there's a typo there too, have a defect. If the tire has a defect, its life expectancy takes a normal distribution of 30 with a mean of 37 and a standard deviation of 2 in thousands of miles. So that's interesting. A normal tire has a life expectancy that takes a normal distribution of 44,3. In other words, it has an average lifespan of 44,000 miles with a standard deviation of 3,000 miles. So here's our question. What's the probability a randomly selected tire lasts less than 38,000 miles? Let's figure this out. Well, let's organize this information. I'm telling you right now, we could organize this in a tree. So let's organize this. Let's see here. So we know, first of all, that these tires either have a defect or they don't. So let's say here's defect. Here's just a normal tire. There's a normal tire. And we know the probability of a defect was 5%. So the problem of a normal tire is going to be 95%. Okay. And then we said that if a tire has a defect, right, it has this normal distribution, right? So its life expectancy is a normal distribution with a mean of 37,000, a standard deviation of 2. Similarly, if it's a normal tire, it's a mean of 44,000 and a standard deviation of 3. But notice that really what I'm thinking about here is this question. I'm really asking this probability. I want to know the probability that basically the life expectancy, let's call it X, right, is less than 38,000 miles, which we could just write as less than 38. Well, that becomes the point of reference then for both for me thinking about these situations. I could say, well, like in the world where the tire has the defect, right? Then I can say I've got some. I can calculate a probability based on this normal distribution right here, the mean of 37 and a standard deviation of 2. 1, 2, 3, 1, 2, 3. And I could say, all right, so 30, this would be like 39. So 38,000 miles in this world would be right about there. And I could see that the probability of that is going to be a little bit more than 50%. More than a 50% chance that a tire will last less than 38,000 miles if it has a defect. Right? All right. Well, let's think about what is that actual probability though. Let's go into our calculator and calculate it. So I'll hit second vars, normal CDF. I'll do everything from negative infinity to my upper bound. Let's say that's 38. The mean was 37. The standard deviation was dose. Let's hit paste and 69.146. So that's the probability of that, 0.6914. 6%. So pretty high probability of a defect there. All right. Well, let's say, what about in the other world? The other world where the tires are just perfectly normal, right? Where they don't have this defect. Well, and then in this world of in this normal world, the normal distribution has a mean for the life expectancy of the tires, mean of 44, the standard deviation of 3. So let me label 3 standard deviations. And if I start going back, 44 minus 3, that's 41. Subtract 3 again. Well, that's 38 right there, right? And so I can shade in everything in this distribution. Here, I'll use blue for this one. Everything there is 38. I shade everything this way. Well, I can estimate that that would be like, what, around 2.5%? Because that's just below 2 standard deviations, but it's not exactly 2.5%. Let me calculate it anyways. Go to normal CDF. I could say, all right, this time I have a mean of 44. And a standard deviation of 3. I'll hit paste. And Shazam, it's like 2.275%. So there's my probability, 0.0225. So there we go. All right, now you might be like, all right, well, I know in the world of defects, the probability that the tire lasts in 38,000 is about 69%. I know it's really, really low probability in a normal world. How do I put these together? Well, duh, I just follow the paths, just like always, right? So I could say, okay, the total probability of getting something, getting a tire that with a life expectancy less than 38,000, oh, no worries, is going to equal the sum of these two particular cases. That'll be 0.05 times 0.69146, right? That was this first path. This first path to that event happening. And then similarly, I can add to that the second path, right? The second path was 0.95 normal tire times 0.02275, right? And that's that second path towards having a tire less than 38,000 miles. And so if I want my total answer, I'll just start multiplying. I'll go, okay, Mr. Calculator, 0.05 times 0.69146 plus 0.95 times 0.02275, and I get 0.056, 0.056, say round that off to 2, and boom, that's my probability. What's the probability that a tire lasts less than 38,000 miles in general? About 5.62%, right? If I given that the tire was a normal tire, it would be lower than that, 2.275. Given that the tire had the defect, whoa, it was a much, much higher probability of that thing happening. Overall, the probability that the tire lasts in 38,000 miles is right there. Pretty cool. All right, so those were the three problems that I kind of wanted to go over today. For your assignment today, you're just going to do some practice, in particular working with tree diagrams, but also occasionally also potentially using some Venn diagrams when it becomes necessary as well too, or even busting out some stuff with normal distributions because, hey, now we're really having fun. Have a very beautiful afternoon, and I will catch up with you guys. Adios.